Greetings of the day to all of you. Today I'm going to continue my discussions on Statcom. I'll write here Statcom, and we are going to continue our discussions from where we left in the last lecture. In the last lecture I have discussed with you that, and I have told you that Statcom is basically a converter based shunt compensator. It comprises of a three-phase voltage source inverter, and by inverter output voltage control with the help of modulation index control, we are able to exchange reactive power with the transmission bus to which it is connected in parallel. And if phase angle between the inverter output voltage and the bus voltage is controlled, we can also exchange active power provided the DC bus is having energy storage like battery energy storage system, etc. I discussed with you that the Statcom behaves just like a rotating synchronous condenser, which is basically a synchronous machine used for reactive power control, okay, which is also called synchronous condenser. And I have discussed, and I hope that you already know that when a synchronous condenser is overexcited or underexcited, it exchanges reactive power with the system. Let us try to understand that concept again with the help of phasor diagrams. So let us draw phasor diagrams. We'll try to understand how a synchronous condenser injects or generates the reactive power, and how does it absorb the reactive power depending upon the DC field excitation. So this is the schematic diagram. This is our synchronous machine or synchronous condenser, which is interfaced with the AC transmission system or AC bus having voltage V. The voltage output of synchronous condenser is E. The field current flowing in the field winding of the machine is IF, and this field current is controlled with the help of static excitation control, which is shown with the help of this block. Let us assume that a current I flows between the AC bus and the machine, and the reactance of machine or machine output voltage is interfaced, or it is coupled with the AC bus voltage through an interfacing reactor X. Okay, now let us take case A. Case A is that the machine is overexcited. The machine is operating in overexcited mode. Overexcited means that your excitation control increases the field current in the field winding, and hence increases the machine generated voltage, which ultimately becomes greater than V. So E becomes greater than V. That means machine generated voltage becomes greater than the bus voltage to which it is coupled. Okay, equivalently it will look like this. This is AC bus to which machine is interfaced through this reactor JX, and EMF induced in the machine is E, and the current flowing is, say for example, I. To be to make it more clear, the AC bus can be shown as a source having a voltage V, and this AC bus is interfaced with the synchronous condenser whose generated voltage is E, and the current, let us suppose, is flowing in this direction. Why I am showing current in this direction, why not in this direction, you will understand in a minute's time. Now if you apply Kirchhoff's voltage law in this circuit, okay, I will write here by Kirchhoff's voltage law, KVL. We can start from here. E, we can start from here, minus V. Okay, if I start from here, or if I start from here, minus E. When you go from negative to positive, the sign is taken as negative. Minus E plus, since current is flowing in this direction, the voltage drop across the reactance is Ix and it is positive. So plus Ji into X plus, again you are going from positive to negative, so plus V is equal to 0. So minus E plus Jix drop plus V is equal to 0. This is by Kirchhoff's voltage law. And from this we can find the synchronous condenser generated voltage or machine generated voltage E. It is simply equal to V plus Ji into X. This is a very important relation. Or equivalently, we can also say that V is equal to E minus Ji into X. Okay. So therefore, the phasor diagram will look like this. Let me show the phasor diagram. Let me draw the phasor diagram. So I have two equations. Let me draw the equivalent circuit again. This is E, this is flow of current I, and this is V. Okay, so I am discussing case A, and case A is overexcitation E greater than V. And what are the equations I just, by applying KVL, what equations I got? I got E is equal to V plus Ji into X. And I got another equation for V. V is equal to E minus Ji into X. If you now draw the phasor diagram, you can either take E as reference or V as reference. Let me take E as reference. The choice is yours. You can take even V as reference. Taking E phasor as reference. Okay. So this is E. Right? Now, I have already told you in the last lecture also that when the synchronous condenser is overexcited, it draws leading power factor current. That means the current which flows between the machine and the AC bus I, it is at leading power factor. It leads the voltage by 90 degrees. So therefore, where will be this current? This current I will be here. And you can see the current I leads the voltage E by 90 degrees. Because when the machine is in overexcitation state, when the machine is overexcited, the system sees the machine as a capacitor. The machine draws this leading power factor current I. In other words, it generates the reactive power and injects that reactive power into the AC bus. So the current I is leading E by 90 degrees because this current is at leading power factor. Okay. Now, because of this current, there will be voltage drop across this reactance. Okay. Now that voltage drop is through this reactance, and we know that this is a pure inductance. Considering this reactance as a pure inductance, the voltage in an inductance leads the current by 90 degrees, or current lags the voltage by 90 degrees. That means if this is the current I flowing through this reactor X, the voltage will be V, and this voltage will lead the current by 90 degrees, or in other words, current will lag the voltage by 90 degrees, or you can show it like this, I and V. So I is lagging behind V by 90 degrees, or in other words, I should, instead of writing V, I should write Ji into X. The voltage drop across this reactor is Ji into X. So this is Ji into X. So whether we take this phasor diagram or this phasor diagram, if I is the current flowing through the reactance X, which is a pure inductance, the voltage drop across this reactance is Jix, and that leads the current by 90 degrees, or in other words, we know that in an inductor, current lags behind the voltage by 90 degrees. So therefore, if I is the current flowing through this reactor, the voltage drop across this reactor will lead the current by 90 degrees. So that will be in this direction. So this is Ji into X. So assuming that all the phasors are rotating in the counterclockwise direction, so counterclockwise rotation clearly shows that this voltage drop Jix through this inductance leads the current through the inductance by 90 degrees, or in other words, current I lags behind the Jix drop by 90 degrees. Okay. So therefore, what is V? As per this equation, what is V? V is E minus Jix. So if this is E, so from this E, you have to subtract this Jix, and you can see Jix is in this direction. So from this, you have to subtract a vector, a phasor whose length is equal to Jix, and which is in this direction. So this is Ji into X drop. So E minus this Jix drop will give you V, which is the AC bus voltage. Okay. So taking E phasor as reference, current I leads the voltage by 90 degrees. Okay. and then JIX drop leads the current by 90 degrees, and this JIX drop is in this direction, and it subtracts from E. The length of this phasor is same as the length of this vector, so this will give you V. So you can very clearly see that V is equal to E minus JIX, or in other words, E is equal to V plus JIX. Okay, so it satisfies these equations. That's why you have to take this current at leading power factor. If you take this current at any other power factor, for example lagging power factor, then these equations will not be satisfied. Okay, then this condition that E is greater than V will not be satisfied. So from this phasor diagram, you can very clearly see that E is greater than V, because you have overexcited the machine. By controlling the excitation of the synchronous machine, you have made E greater than V. And in order to satisfy this condition that E is greater than V, V should be E minus JIX, and that is possible only if it draws a leading power factor current. So it draws the leading power factor current I, and that makes E greater than V. So therefore E is equal to V plus JIX, or V is equal to E minus JIX. So this phasor diagram clearly shows that in the overexcitation state, when the synchronous condenser is overexcited, making E greater than V, this is the phasor diagram. And phasor diagram clearly shows that why it draws leading power factor current, because when the machine is overexcited, it draws leading power factor current that makes E greater than V. Otherwise, E will not be greater than V. Okay. So to satisfy this condition that E is greater than V, the machine has to draw the leading power factor current. So I hope that is clear. Okay. So this is case A, when the machine is overexcited. Let us quickly go to case B, when the machine is underexcited. Case B. In case B, we assume that the machine is now underexcited. So in overexcitation mode, E is greater than V, there is a leading power factor current, and leading power factor current means that the synchronous condenser is generating the reactive power and injecting that reactive power into the AC bus. Okay, that is for overexcitation. Now in case B, underexcited case, the excitation of this machine is again controlled. In fact, the field current is decreased in order to make E less than V. So when the machine is underexcited, the machine induced voltage or generated voltage is less than the AC bus voltage. E is less than V. So this is underexcitation condition, right? Now, therefore now current will be in this direction. Instantaneous value of current or instantaneous direction of current you have to take in the opposite direction, which means that if this is the capacitive current IC, which was case when E was greater than V, the IL current will be like this, where this is the current when E is less than V, because I have told you when the machine is underexcited, when synchronous condenser is in underexcitation mode, E is less than V, at that time the current lags behind the voltage by 90 degrees, or it draws the lagging power factor current. That means it is absorbing the reactive power. So therefore, if this is the leading power factor current, this is the lagging power factor current, which means that the two currents are 180 degrees out of phase with each other. Previously, for overexcitation scheme, I had taken this direction of current, instantaneous value of current, and for underexcitation, I have to take opposite direction of the current, because the leading power factor current and lagging power factor current are opposite to each other. If this is lagging power factor current, this will be leading power factor current, opposite to each other. Okay, this is IL, this is IC. Okay, so that's why in this diagram I have changed the direction of current, because I know that when the machine is underexcited, it draws lagging power factor current. Why does it draw lagging power factor current? Why not leading power factor current? That will be again clear with the help of phasor diagram, which I am going to draw now. Now let me apply this Kirchhoff's voltage law again here by KVL. Now I can start from here. So minus V, when I go to minus to plus, minus V plus this drop is now like this, because current is flowing in this direction. So drop is positive because you are going from positive to negative. So Ji into X plus Ji into X, and then again you are going from positive to negative, plus E is equal to 0. So minus V plus JIX plus E is equal to 0. So this will give me V is equal to E plus Ji into X. And this will also give me E is equal to V minus Ji into X. This is what I get. I get two equations. So since V is equal to E plus Ji x, or E is equal to V minus Ji into X, so therefore this clearly shows that E, the synchronous machine generated voltage, is less than the AC bus voltage by the drop. So this shows that E is less than V, and it will be clear with the help of Phasor diagram also. If I draw the Phasor diagram again, now this is again I am taking E as Phasor E as reference. When I take Phasor E as reference, let me take Phasor E as reference. Now current, when the synchronous condenser is under excited, it draws lagging power factor current. This is the current that it draws, and this current lags behind the machine generated voltage by 90 degrees. So therefore, assuming that all the phasors are moving in the counterclockwise direction, this current will cause a voltage drop in this inductance. And from the basic theory of an inductance, current in an inductance lags behind the voltage across inductance, or voltage across the inductance leads the current. So therefore, if this is the current through the inductance, this will be the voltage across the inductance Ji into X, and you can see this voltage is leading the current by 90 degrees, or in other words, current through the inductance or reactance is leading behind the voltage drop across reactance by 90 degrees. So therefore, if this is E, now this Ji into X drop having this much of length is in this direction, so it will be in this direction, and its length will be same as this, so this is Ji into X. So therefore, what is this? This is V. So therefore, it clearly shows that V is equal to E plus Jix. V is equal to E plus Jix. Or in other words, E is equal to V minus Jix. E is equal to V minus Jix, which clearly you can see makes E less than V. So therefore, the condition for under excitation is that synchronous condenser voltage is less than the AC bus voltage. E is less than V. And that will be satisfied only if the machine draws lagging power factor current. That is very much clear from this Phasor diagram. So that is why when the synchronous condenser is under excited, making E less than V, it draws lagging power factor current, and it absorbs the reactive power from the system. It does not inject the reactive power from the system, it absorbs reactive power from the AC bus from the system, and the system sees it as an inductor, right? So this explains how a synchronous condenser exchanges reactive power with the AC bus to which it is connected. By over exciting it, it generates the reactive power, injects that reactive power into the bus, acts as the system sees it as a capacitor. And when the same synchronous condenser is under excited, at that time it draws the lagging power factor current, hence it absorbs the reactive power from the system, and system sees it as an inductor. So this is about synchronous condenser, and I have told you that Statcom works in the same manner as a synchronous condenser. Statcom is also a condenser, but it is a static synchronous condenser or static synchronous compensator, Statcom. Let us draw the Phasor diagrams for Statcom also. Phasor diagrams. So this is the schematic diagram. This is my Statcom converter. It may be a two-level voltage source inverter or a multi-level voltage source inverter, DC bus CDC capacitance with DC bus voltage VDC, and AC inverter output voltage is, let's say, V0 dash, and AC bus voltage is V. Current between AC bus and inverter is I, and the interface reactance is Jx. The inverter or Statcom, this is our Statcom inverter. It is interfaced with AC bus through this interfacing reactance, which may, again, I repeat, it may represent the leakage reactance of the interfacing transformer through which this Statcom is interfaced or connected in parallel with the AC transmission line or AC transmission bus. I am not showing that transformer here. Okay, so equivalently it will look like this. This is the inverter output voltage, say V0 dash. This is, say, for example, the current I. Okay, this is the current I, and this is the AC bus voltage V, and this is reactance. or equivalently I can show it like this. This is the inverter output. This is the AC bus voltage V. This is AC bus voltage. This is interface reactance Jx, and this is inverter output voltage V0 dash. And let us assume current is flowing in this direction. Now again, I can control the modulation. This Statcom inverter is basically a PWM voltage source inverter, and I can control output voltage of inverter by controlling the modulation index. By controlling the modulation index, I can make inverter output voltage V0 dash greater than AC bus voltage, or I can make it less than AC bus voltage. Let me take case A. Case A is I increase the modulation index of inverter, making V0 dash greater than V. That's inverter output voltage greater than AC bus voltage. This is similar to overexcitation of synchronous condenser. Okay. So when this is the case, apply KVL here. So by KVL, the equation is, you can start from here. So minus to plus is minus V0 dash plus current is in this direction. So Ji into X, then plus V is equal to 0, which will give V0 dash equal to V plus Ji into X. And equivalently, this will also give V equal to V0 dash minus Ji into X. These are the two equations that I get. So therefore, this clearly shows that the inverter output voltage V0 dash is greater than V, because it is V plus drop across this reactor Jix. So that clearly shows that the leading power factor current should flow, and it will be clear with the help of Phasor diagram. Let me draw the Phasor diagram, and let me take this V0 dash inverter output voltage as this phasor as reference. So when V0 dash is greater than V, the system sees the Statcom as a capacitor. So Statcom draws a leading power factor current. Leading power factor current means the current I leads the voltage, inverter output voltage V0 dash by 90 degrees. So therefore, when this leading power factor current flows through this interface reactor, it causes a voltage drop across this reactor Ji into X. And voltage drop across an inductor leads the current through it by 90 degrees, or in other words, current through an inductor leads behind its voltage drop by 90 degrees. So you can say I is lagging behind Jix drop by 90 degrees, or in other words, Jix drop is leading the current by 90 degrees. So therefore, if this is Jix drop through this, this Jix drop is in this direction. So I can show this phasor of this length Jix in this direction. So therefore, what is this length of the vector? This is V0. So therefore, this is V, sorry. Why should I write V0 dash? Let me write V0. So this is V0 and this is V. So this is V. So this is V, not V0 dash. So this is V0, this is V. So if this is V0, this will be V. And you can very clearly see that V is less than V0. V is equal to V0 minus Jix. V is equal to V0 minus Jix. It satisfies this equation. And what about V0? V0 is V plus Jix. V0 is V plus Jix. So this clearly shows that inverter output voltage, Statcom output voltage is greater than the AC bus voltage. And to satisfy this condition is satisfied only if Statcom draws leading power factor current, I. Okay. So that is why when Statcom output voltage V0 is made greater than AC bus voltage, the Statcom draws leading power factor current I, and hence that means it generates the reactive power and injects that reactive power into the AC bus, and hence the system sees it as a capacitor. This operation or this performance is similar to a synchronous condenser in overexcitation state. When a synchronous condenser is overexcited, we get the similar phasor diagram and we get the same conditions. There we get E greater than V, here we get V0 greater than V. And when V0 is greater than V, I is leading power factor current, and hence Statcom is seen as a capacitor by the system. It draws leading power factor current, and hence it injects the reactive power, it generates the reactive power and injects that reactive power into the AC bus. Okay. So this is for case A. Let us quickly draw the phasor diagram for case B. Case B. In case B, we are making inverter output voltage by reducing the modulation index of the inverter. We are making V0, inverter output voltage, less than the AC bus voltage. So V0 is made less than V. This is similar to synchronous condenser. when synchronous condenser is under excited. And synchronous condenser output voltage E is made less than V, which we have discussed just few moments back. Now when V0 is less than V, then the system sees the Statcom as an inductor and it draws lagging power factor current. So therefore, if leading power factor current is instantaneous direction of leading power factor current is taken this, the instantaneous direction of lagging power factor current will be opposite, because inductive current is opposite to the capacitive current. So instantaneous direction of the current will be opposite to the first case. So it will be in this direction. So apply the KVL to this circuit. So we can start from here. So my negative to positive when we travel, so it is minus V, plus this drop is JIX because current is in this direction, so it is plus minus. Plus minus, so plus V0 is equal to 0. So this will make V equal to V0 plus JI into X. That means the AC bus voltage is greater than the inverter output voltage by how much? By this drop. Or in other words, we can say inverter output voltage is AC bus voltage minus JI into X. That means the inverter output voltage is less than V by this drop. So that means V0 is less than V. So let us draw the phasor diagram. Phasor diagram will be like this. So again, inverter output voltage phasor is taken as reference. And we assume that now when the Statcom output voltage is made less than V, it draws the lagging power factor current. So current I lags behind the voltage by 90 degrees. So I is lagging behind V0 by 90 degrees. So this is okay. So when this current is flowing through the inductor, through this reactor, it will cause a voltage drop JI into X. And this voltage drop through the reactor leads the current by 90 degrees, or in other words, current lags behind this voltage drop by 90 degrees. So that's why I am showing it in this direction. So if this voltage drop JI into X is in this direction, take equal length of phasor or vector in this direction because it is in this direction. So this represents JI into X drop. So therefore, what is this? This is V. There's the AC bus voltage. So you can very clearly see that the AC bus voltage is inverter Statcom output voltage plus drop. So V is equal to V0 plus JIX. V is equal to V0 plus JIX, which satisfies this equation. Or V0 is equal to V minus JIX. V0 is equal to V minus JIX. So this makes V0 less than V. So V0 is less than V. So therefore V0 less than V, this condition is satisfied only when Statcom draws lagging power factor current. So therefore when Statcom output voltage is made less than the AC bus voltage, it draws the lagging power factor current from the system, and hence it absorbs the reactive power from the AC bus, and hence the system sees it as an inductor. So this is how reactive power can be generated if V0 is made greater than V and injected into the transmission system, or reactive power can be absorbed from the transmission bus if V0 is made less than V. We have proved it with the help of these equations and with the help of phasor diagrams. And in all this case, during this, while studying this, you must have seen that when V0 is less than V or V0 is greater than V, there is exchange of reactive power with the AC bus. So whether the Statcom injects the reactive power into the AC bus or absorbs the reactive power from the AC bus, the two voltages are in phase. You can see in this case V0 and V, they are in phase. Magnitudes are different, but they are in phase. So therefore, for reactive power exchange, V0 and V have to be in phase. Only their magnitudes will be different. However, for active power control, which I have told you in the last class also, if there is an energy storage here for active power control, or for, I will write here, for active power exchange with the system, there has to be a phase angle between Statcom output voltage and V. So if this is your V phasor and this is V0, if V0 leads V by certain angle, it may be 10 degrees, 5 degrees, then what happens? And if there is an energy storage at the DC bus of the Statcom inverter, then that DC power is taken by the Statcom inverter, converted into AC power, and that is supplied to the AC bus. In that case, active power is supplied to AC bus. And if reverse is the case, that means if V0 is less than V, V0 lags behind V. Here V0 leads V. If V0 lags behind V, then what this Statcom inverter does, it takes active power from the AC bus, and that is of course AC power, converts that into DC and dumps that DC power into the capacitor, if there is a capacitor, for charging of capacitor, or if there is a battery bank, the battery bank is charged. So if V0 lags behind V, P is taken, the active power is taken from, or instead of using the word taken, I should use the word drawn from AC bus. So if in Statcom output voltage leads the AC bus voltage, then Statcom power is supplied to AC bus, and if Statcom output voltage lags behind the AC bus voltage, power is drawn from the AC bus. Okay. And for reactive power control, I already told you that the phase difference between V0 and V should be 0, they should be in phase. However, for supplying the losses of the GTO or IGBT switches, the converter switches, V0 generally, it lags behind V by a very small angle, even when reactive power exchange takes place, say 0.1 degree to 0.2 degree, so that it continuously takes small active power to supply those switching power losses and conduction losses of the switches of the inverter, so that DC bus capacitor voltage is maintained constant. Okay, so that is it. So therefore, by controlling the magnitude of Statcom output voltage, reactive power exchange takes place, and by controlling the phase angle between the two voltages, active power exchange takes place between Statcom and AC bus. And the beauty of Statcom is that it can simultaneously exchange active power as well as reactive power with the AC bus to which it is interfaced. So there is the possibility of simultaneous exchange of active power and reactive power. So that I can show with the help of this simple diagram. In the first quadrant, Statcom supplies the active power. So here I will write supplies active power and supplies reactive power also. Okay. In the second quadrant, it absorbs reactive power. It does not supply reactive power. It absorbs reactive power. It absorbs the active power, but it supplies reactive power. In the third quadrant, the Statcom absorbs active power as well as reactive power. Absorbs active power, and I should write absorbs reactive power also. And in the fourth quadrant, the Statcom absorbs reactive power and supplies active power. So I will write here supplies active power and absorbs reactive power. We know that reactive power exchange takes place when V0 is less than or greater than V. When V0 is greater than V, reactive power is supplied, and when V0 is less than V, reactive power is absorbed. And delta, if it is positive, that means V0 leads V, and delta may be negative, that means V0 lags behind V. And if delta is positive, that means V0 leads V, active power is supplied. And if delta is negative, that is the phase angle between V0 and V is negative, that means V0 lags behind V by some angle, then active power is absorbed. You can make your Statcom to supply active power as well as reactive power to the AC bus. How does it supply reactive power? In that case, V0 will be greater than V. Statcom inverter output voltage you can make greater than V, and it supplies reactive power. And how does it supply active power? Let me tell you again, it will supply active power only if there is an energy storage on the DC bus. And in that case, it can supply active power only when delta is positive. That means V0 leads V by certain angle, phase angle delta. Okay. Now we can make it operate like this. We can make it absorb active power. How can it absorb active power? if delta is negative. Delta is negative means we can make V naught lagging behind V. That is possible, and in that case it will absorb reactive power, and it can supply active power by making V naught greater than V. And in the third case, we can make it absorb active power as well as reactive power. That means delta will be made negative and V naught will be made less than V. When V naught is less than V, it absorbs reactive power. And in the fourth case, we can make it supply active power. Active power is supplied when delta is made positive and absorb reactive power. Reactive power will be absorbed when V naught is less than V. So for supplying active power and reactive power to the AC bus, this is the condition. Your controller should make V naught greater than V and it should make delta positive. For absorbing active power from the AC bus and supplying reactive power, your controller should act like this. It should make delta negative and V naught greater than V. For absorbing active power as well as reactive power, your controller should make delta negative and V naught less than V. And for supplying active power and absorbing reactive power, your controller should make delta positive and V naught less than V. Okay. So therefore, simultaneous active as well as reactive power control can be done with the help of Statcom, which is not the case with SVC. SVC can exchange only reactive power with the AC bus, not active power. But Statcom can exchange active power as well as reactive power with the AC bus to which it is connected. And now let me briefly discuss with you VI characteristics of Statcom. The beauty of Statcom is that it maintains the reactive current. Reactive current may be leading power factor current or lagging power factor current, depending upon whether it is generating reactive power or absorbing reactive power, whether it is supplying reactive power to AC bus or absorbing reactive power from AC bus. It keeps the current constant independent of the AC bus voltage. So that will be clear with if we draw the VI characteristics like this. This is inductive current IL and this is capacitive current IC. Here in this region the Statcom acts as an inductor, so this shows inductive operation, and here it shows capacitive operation, capacitive mode of operation. In this region the Statcom absorbs the reactive power from AC bus, and in this region it supplies reactive power to the AC bus, and this is AC bus voltage. Let me show you the currents. The currents will be like this. Let me first of all draw one. So this is let's say voltage is in per unit. So this is 1 per unit. This is 0.75 per unit. This is 0.5 per unit. 0.25 per unit. 0.15 per unit, and then it will collapse. So you can see this is IL max, maximum inductive current. Let me first of all draw, then I will explain. And this is IC max. This is IC max, maximum capacitive current, which is generated by Statcom. And the Statcom has some transient rating also. I mean, for a period, small period, it can supply the reactive current more than its maximum rating current. This is called transient rating. It has got, from here to here, it has got transient rating, and it can supply the inductive current greater than IL max for t less than 1 second. 1 second. Similarly, in the capacitive mode of operation also, it has some transient rating. This is the transient rating. I should write here transient rating. This it can supply capacitive wires or capacitive current greater than IC max for some small period t less than 1 second. Okay. Now you can see if the AC bus voltage to which your Statcom is connected, if the AC bus voltage is rated voltage, I mean 1 per unit, then this is the, if your Statcom is operating in the inductive region or capacitive region, this is the current. Depending upon how much reactive power has to be, absorbed from the AC bus in this region, because in this region it acts as an inductor, in this region it acts as a capacitor, or how much reactive power it generates and injects into the AC bus, it draws certain amount of current, and this is the current at different values of current at this voltage. Will it, while operating in the inductive range, will it have this much of current or this much of current? That depends upon how much reactive power it has to absorb. Or in the capacitive mode of region, whether it will operate at this much of capacitive current, this much of capacitive current, or this much of capacitive, or maximum limit of the capacitive current. That depends upon how much reactive power it has to inject or supply to the AC bus. Now suppose the AC bus voltage collapses a little bit due to some fault or due to certain conditions. The AC bus voltage decreases from 1 per unit to 0.75 per unit. So there is a drop of 25% of AC bus voltage. But you can see, even if the voltage drops, if it was operating here, the current does not change. If this was the current IL dash, or in the capacitive region of operation, if this was IC dash, irrespective of whatever is the voltage of the AC bus to which Statcom is connected, the current remains constant. When the voltage decreases by 50%, the current still remains constant. When the voltage drops to only 0.25 per unit, the current is still constant till voltage drops to as low as 0.15 to 0.12 per unit, and it maintains the current constant. But if the voltage is below 0.12 per unit, okay, then the current will drop. I mean, there will be decrease in the current, sharp decrease in the current. But 0.12 per unit or 0.15 per unit means the voltage has collapsed by about 85%, okay, which is there because of a huge fault. So therefore, if the AC bus voltage changes, it drops, whether it decreases or increases, the current drawn by the Statcom is independent of the AC bus voltage. This is one of the very important features of Statcom. So the current drawn, it may be inductive current or capacitive current by Statcom. When will be it inductive current? When it absorbs reactive power. And when will be it capacitive current? When it generates and injects reactive power into the AC bus. So current drawn by Statcom is constant and independent of AC bus voltage. It is very much clear from these VI characteristics of Statcom. Okay, whatever is the voltage of the AC bus, the current remains constant. Okay, if this is the operating current, it remains constant independent of the voltage. Whereas in SVC, you will see that the SVC also draws current from the AC bus. The current drawn by SVC is linearly changed with AC bus voltage. If AC bus voltage decreases by 30%, the current drawn by SVC also decreases by 30%. Whereas in Statcom, the current drawn by Statcom is independent of the AC bus voltage, it's constant, which makes Statcom a more effective compensator, shunt compensator than SVC, which we will discuss that hopefully in next lecture, when we will compare, we will draw a comparison between the two types of shunt compensators, that's Statcom and SVC. So this is about VI characteristics. And finally, to wrap up my lecture, a little bit about Statcom converter. We know that Statcom is nothing but it is a voltage source converter. What type of converter is used? You may use 3-phase 2-level voltage source inverter or voltage source converter, or you may use 3-phase multi-pulse converter or inverter, or you may use 3-phase multi-level converter or multi-level inverter. Okay, if you use 3-phase 2-level inverter, the power circuit diagram is something like this. Let me first of all draw, then I will explain. These are the devices. This is DC bus voltage VDC. It's a 2-level inverter, and AC bus is like this. This is phase A terminal, phase B terminal, and phase C terminal, and these are the reactors. And it is connected to the AC bus. This is AC bus here. This is AC bus. Okay, this is a 3-phase 2-level 2L means two-level voltage source inverter. But generally, two-level voltage source inverters are not used for Statcom because Statcom is connected across the transmission lines. It's not used at the distribution level. It is to be used at transmission level, and transmission level voltages are very, very high, of the order of hundreds of kV. And even if you use a step-down coupling transformer, the medium, and convert the high voltage compensator bus into medium voltage compensator bus and connect your Statcom, the voltage, medium voltages, even if that voltage is very, very high, that may again be hundreds of kVs, kilovolts. So two-level inverters are suitable for low voltage applications. Therefore, two-level inverters are generally not used. So therefore, I will put a cross. Two-level inverters are not used for Statcom. Then I am left with multi-pulse inverter and multi-level inverter. Before the advent of multi-level inverters, multi-pulse inverters have been investigated and they have been widely used for Statcom applications. For example, one of the most popular multi-pulse inverter which has been used as Statcom is 48 pulse voltage source inverter, and it produces this type of voltage like this in the form of staircase. The total number of these steps are 48, but since I don't have space, I am drawing less number of these levels or pulses, and it approximates a sinusoidal voltage. It's very close to a sinusoidal voltage. This is AC line voltage, actual voltage. And this is Statcom voltage generated by Statcom. This is Statcom output voltage, which is multi-pulse voltage. Okay, 48 pulse means there are 48 pulses in one cycle, and it is very close to sinusoidal voltage. Therefore, the advantages of 48 pulse or multi-pulse voltage source inverter is that it produces the output voltages which are very close, which are approximating to the sinusoidal waveforms if higher number of pulses like 48 pulses are used. And secondly, we can use it for high voltage applications. But these multi-pulse inverters have been now taken over by multi-level inverters. Nowadays, for Statcom converter, multi-level converters are very, very popular, and we already know that there are broadly three types of multi-level converters: diode clamped multi-level converter, flying capacitor multi-level converters, and cascaded H-bridge multi-level converters. So these are different types of multi-level converters which are very popular for medium voltage and high voltage applications. And since Statcom converters have to be connected through the interfacing transformer or coupling transformer directly to the transmission system, which is at a very high voltage, so multi-level converters or multi-level inverters are very popular converters for Statcom converters, for Statcom applications. And among the three types of multi-level inverters, the most popular multi-level inverter is cascaded H-bridge inverter, cascaded H-bridge multi-level converter or multi-level inverter, cascaded H-bridge multi-level converter, CHB MLC, because it has least device count. I have already discussed with you in details in second semester, spring semester, in the previous semester, in the course on pulse width modulation techniques about these types of multi-level converters. We have spent a lot of time understanding the topography or topology and operation of these three types of multi-level inverters. I don't need to repeat that here. You can revise those operation and topologies of these multi-level inverters going back to those lectures. They are available on my YouTube channel. And for those who are new to this course, who have not attended my last semester course on PWM techniques, the 2 to 3 or 4 lectures are available on my YouTube channel on multi-level inverters or multi-level converters. So among the multi-level converters, cascaded H-bridge multi-level converters, CHB MLCs, are very popular for Statcom applications. So that's all about Statcom. So therefore Statcom is nothing but it is a shunt compensator. It's a converter based shunt compensator. It behaves like a synchronous condenser, but since it does not have any rotating parts, it's static. That's why it's called static synchronous condenser or static synchronous compensator. StatCon or StatCom. It's basically nothing but a three-phase voltage source inverter. It's a multi-level inverter which converts DC into AC, and the inverter output voltage or Statcom output voltage is coupled and is in phase with the AC bus voltage. It is coupled to that AC bus voltage through the interface reactor X. Okay, and just like a synchronous condenser, if inverter output voltage is made greater than V, it acts as a capacitor. It generates the reactive power, injects that reactive power into the AC bus, and if inverter output voltage V0 is made less than V and is in phase with V, it acts as an inductor, and it draws the reactive power, absorbs the reactive power from the AC bus. And for active power exchange, if inverter Statcom output voltage leads the AC bus voltage by a certain phase angle delta, the AC power is supplied to the AC bus, provided the energy storage is available on the DC side of the Statcom inverter, DC bus of the Statcom inverter. And if V0 inverter, the Statcom inverter output voltage lags behind the AC bus voltage V by phase angle delta, then it absorbs or draws the active power from the AC bus. Okay, so therefore it behaves like a synchronous condenser, and active power control as well as reactive power control can be done, and in fact simultaneous active as well as reactive power control can be performed by Statcom, which cannot be done by SVC. Regarding VI characteristics, we have drawn VI characteristics also, and we have seen that from the VI characteristics that the Statcom reactive current drawn by the Statcom is independent of the bus voltage. And finally, I have told you that what type of converters are suitable for Statcom applications. So it is multi-level converters, and among the multi-level converters, cascaded edge bridge multi-level converters, CHB MLI or CHB MLC, they are very popular for Statcom applications. With this, we conclude our discussions on Statcom. In our next lecture, we will try to draw a comparison between Statcom and SVC, which are two shunt compensators. Statcom is converter-based shunt compensator, and SVC is thyristor-based shunt compensator. We will try to draw a comparison between the two, and we will try to see the features of both and make a comparison between the two. So I wish all the best to all of you. Thank you.